Hello, it's Scott Manley here, and this is NASA's Vertical Gun Range. This is a unique scientific facility, and I'm here to watch them shoot some space rocks.
So as you might guess from the name, the vertical gun range is a gun which can shoot things vertically, but vertically downwards into targets. And it can shoot the projectiles at velocities, comparable to orbital velocity, whereas your average assault rifle might throw bullets at maybe 700 meters per second. This can shoot projectiles at maybe 5 to 6 kilometers per second. And that's critical for reproducing collisions that may happen in space. And if you've been watching my channel for a long time, you probably know that you can't simply put bigger bullets in a gun to make it go faster. You start to reach physical limits. Now, these shells, those are left over from 2 kilometer per second tests. They have that ability if they need to go that slow, but if they want to go faster, they need a 2-stage light gas gun. So this critically important facility was built in the 1960s for the Apollo program, and it is still used today because it's the only one of its kind in the world. There are other places that have these hypervelocity guns, but this is the only one which can change the impact angle. Hence, it's called the vertical gun range. Right now, this is laid down horizontally because they're prepping it for firing. But once it's loaded and ready to go, they'll raise it to the firing position. Now, when I was there, they only raised it up to 15 degrees, but it is possible to raise it entirely vertical so that it fires straight down. And it fires a projectile into that blue vacuum chamber. Because, of course, you're simulating impacts in space, and because when you've got a projectile moving at 5 kilometers per second, it might get a little hot before it hits the target. The vacuum chamber is also heavily instrumented with the best of the best in terms of high-speed cameras. And for today, the target would be meteorites. Now, normally those come and hit the Earth at many kilometers per second, but we were deciding to give them a taste of their own medicine because the scientists were interested in how collision processes shape the asteroid belt, which is kind of important for planetary defense.
The purpose of it is, in planetary defense, one of the ways they've talked about deflecting an asteroid on a collision course with Earth is to just hit it with an object, very much like the DART mission did last year.
Yeah, kinetic impact.
Kinetic impact. And so there are two things you have to know for kinetic impact. You have to know how much momentum you're going to transfer with the impactor. And it's not the simple physics problem you would think, because you generate crater ejecta, which is basically a rocket exhaust coming out of your target. And so you enhance the momentum transfer, and we're trying to measure how much it's enhanced by from the crater ejecta.
This is your beta value?
This is our beta value, but there's another important thing that the Hollywood people have made very clear, and that is if you break up the target, you may have a piece still coming towards you.
Yes.
And they've depicted that very well, and that's a bad thing to do. And so the second thing we want to measure is how much energy does it take to fragment the target.
And this is fragment a rubble pile or solid rock?
All of what we're doing deals with solid rock.
Okay.
And I think there are a lot of solid rock asteroids out there, especially some of the small ones, which are the ones we have the capability of deflecting. So you have to measure both the momentum enhancement and the energy it takes for fragmentation, because that gives you the sweet spot for how hard you can hit the asteroid, how much deflection you can do with a single impactor. And that's what we're trying to find out.
And so this is obviously a scaled down test against a solid rock.
Scaled down test, but it's on real samples of asteroids.
Oh, real samples of asteroids.
These are meteorites, which are pieces of asteroids.
And these are stony asteroids, presumably.
That's right. Sometimes we get close Earth approaching asteroids that are imaged by radio telescopes.
Yes.
And so we know something about the surface of some of these smaller ones that have come inside the Earth-Moon distance.
And we've seen some that are fast rotators that have to be solid objects.
They have to be solid objects because you would throw, if they were a rubble pile, you would start throwing pieces off just from the rotational velocity, very much like if somebody's swinging a rock on a string and the string breaks, the rock goes flying off.
Right. So anyway, we're working specifically in the domain of objects which are small, therefore more likely to be solid objects, and we're doing that because these are the range in which we can make a difference.
That's right.
On timescales that are reasonable.
The really dangerous ones don't happen very often.
Right.
Really, really big ones like the extinction event for the dinosaurs, it was a several kilometer object.
Yes.
But We can't deflect a several kilometer
We
object.
can if we get thousands of years of warning.
If you get a lot of warning, you can deflect it.
It's all about warning versus
That's right.
capability. I think-
Make a little deflection 100 years in advance,
Yeah.
and it's a big deflection by the time 100 years has elapsed.
Yeah, I think DART has moved Dimorphos by a few hundred kilometers now in the last couple of years. It's not enough to make it. I mean, it might make it miss the Earth, but we need a bit longer warning, or we need a bigger bang. So the targets are supposed to replicate free-floating pieces of rock in space. So in the vacuum chamber, they are suspended on tiny little fibers. And once the pressure there is removed from the vacuum chamber, they will tend to keep swinging. So they have to make sure that these things are absolutely still before they start depressurizing. So while the scientists are getting their side of the experiment ready, the range engineers, they are also at work getting the gun prepped. Now, it comes in multiple parts. There's a very complicated firing sequence to make sure that the cameras are triggered at the correct time. And of course, a lot of essential safety protocols because they are working with explosives and high pressure gas. So just to give you an idea, this is the business end of the gun where the main explosive charge is, and it drives a piston into this next section, which currently isn't in here. And then we have a section which removes the sabot, and that then connects directly to the vacuum chamber. So there's two barrel sections because this is a two-stage light gas gun. At one end, you have the explosive charge and you have a piston, which is typically made of a plastic. And in the case of the vertical gun range, it's about the size of a wine bottle. So the explosive charge activates and then this starts pushing it down the barrel section. In front of it, there is hydrogen gas, and that hydrogen gas is getting compressed as it slides down the barrel. And then it's that hydrogen gas that pushes the actual projectile. Now, this projectile is held inside a sabot, and once it emerges from the rifle barrel, the sabot falls away, and you have a very small projectile moving at 2 to 3 times the speed of a regular bullet.
That's the launch package, the model and the sabot, and this is an installation tool.
This is an installation tool
Yeah, this part here.
to just get it centralized in this whole thing.
Yeah, I
Okay.
can show you.
Okay.
This is our gun barrel. It's
Right.
Rifle gun barrel.
Yep.
So it's like the old James Bond movies, minus Sean Connery. We're older, vintage, so it's a tapered entry here. So we install the installation tool, and then we use the plunger, and then boom, it's in place.
That's it.
And then I'll do a final adjustment because you want to make sure it's a nice snug fit so that there isn't enough slop for the particle to fall out of the sabot.
Yeah.
That feels pretty good.
We're going to do a tandem load and then we'll rotate counterclockwise.
Okay. So we're looking to make sure that nothing falls out the other end.
So this is the high velocity gun barrel that sits in the second stage of the system. And the first thing they're doing is tipping it over to make sure that nothing falls out the other end, because that would be kind of embarrassing. So this barrel fires into the vacuum section of the gun, which then travels down to the vacuum chamber itself.
High pressure coupling coming your way.
Alrighty.
So now we have the massive high pressure coupling. You can see this is pretty heavy duty. This is supposed to capture the piston that has been fired by the first stage gun and contain the gas as it is squeezed down and efficiently transfer it to the second stage projectile without losing pressure.
Pump tube come forward. There.
So now they slid the rear section forward and it's being connected to the high pressure coupling. This obviously has to be sealed because that section is going to contain the high pressure hydrogen which is driving the second stage.
This is a hydraulic clamping mechanism. We put the rupture disc right ahead of your launch package here. And there's a deformable metal seal, and when the hydraulic actuator is engaged, it crushes that seal and makes our pressure tight seal. The reason for that, not an O-ring, is because we have tens of thousands of PSI, so this is what is needed to resist that.
These are transient pressures
Yes,
during firing,
correct.
yes.
Yeah, you're talking millisecond.
Yeah.
Microseconds.
Like gas wants to go places and you want it to go push the projectile.
Yeah.
Seal this one in.
Okay.
This is very similar here, if you want to look at that. We have a flange seal with a burst disc and sandwiched between two steel pieces.
It's worth remembering that they are working with hydrogen, which is famously good at escaping through the tiniest of cracks on the account that it is a very small molecule. You'll notice that when they're setting this up, there's a lot of discrete parts that are used once and then discarded. It's quite a complicated system that has a lot of different pieces.
Headspace is set. Nose in, aligned. Clamp it up and pump it up.
Okay.
What we're doing next is we're going to be bringing up the hydraulics to 3,000 psi to create a seal,
Okay.
and then we can proceed with the leak.
So that space that we normally fill with hydrogen, for our initial leak check, we fill it with helium. Because if it'll not leak with helium, then it'll be good for hydrogen. And if we do have a leak, we'd rather have helium leaking in the room rather than hydrogen.
How do you detect the helium? I guess it's just pressure drops if it.
Right, that's we monitor as long as the pressure doesn't drop within a certain amount, because there's a thermal equilibrium that takes
Yeah.
place. And as long as by observing pressure, we're convinced that it's a tight seal, we're good.
Yeah.
If there's not, we have a high helium leak detector that we sniff around with to figure out.
Okay. So this panel is going to be showing pressure increase.
Chuck is going to do the leak check. We'll vacate the pump tube, bring it down to the vacuum pump, and then he'll perform the backfill with helium.
I always like looking at a good valve panel. It lets you see where everything is being routed.
Okay.
You get a good idea of how the thing operates just by following the lines and the valves.
All of the
Yeah, no, I've seen these stickers.
various missions that we've supported.
Yeah. Osiris-Rex, Psyche, Stardust, Deep Impact, Apollo 11.
Apollo in general and,
Yes.
and Viking, yeah.
Viking. Yeah.
So the initial purpose of the facility was
Right.
to develop that understanding of the lunar surface conditions.
One more time.
And it's probably low enough for a leak.
I think that's about as low as it's going, yeah.
So now with the air removed, it's time to start filling that space with helium so they can do their leak check. So watch as the pressure in that pump tube starts to rise up, and it'll get up to about 6 atmospheres of pressure for this initial test. And for all my viewers who speak metric, 1 atmosphere of pressure is about 14.7 pounds per square inch. So when you see this going up to about 90, that's equivalent to, 6 atmospheres of pressure, more or less.
We need 0.16 psi. We'll come back in 5 minutes and see if it's
9. Okay.
about the same.
Chuck, while you're doing that, can you look the gun to access position?
This is the gun. It's getting ready to fire. Get a step over this here, like. Okay, so we're pumping down the chamber now.
Yep. Down to 5, well, just below 5 millimeters of mercury.
5 millimeters of mercury. What is that in sane units? What?
Let's see, there's 760 millimeters, 760 torr in an atmosphere.
Yeah. So it's about 0.2 inches of mercury. How about that?
Yeah, let's see. We're hoping to get down to about half a millimeter mercury, which is just over a millibar.
Yeah.
Which is a little less than a thousandth of an atmosphere, or thereabouts, in rough numbers.
So this is being sucked out through this. There's a pump out there.
We have two. There's a pump on the wall behind you. There's a pump out here
Okay.
as well. There's 2 pumps and various valves. It's all to do with evacuation rate, depending on the nature of the target. These we can kind of go medium fast, Otherwise, you start just the targets start moving around.
Oh, right, yeah. So you're trying to keep it stable.
Right.
So don't bump this thing, because if I touch this, the whole thing is just going to start rocking, right?
No.
That would ruin the experiment.
Maybe Arnold Schwarzenegger. Maybe he could disturb it enough. But yeah, if the air currents move it and you don't have much in there, there's nothing to restore it or dampen it.
Yeah,
So
it'll swing forever.
So we have to be very gentle in the evacuation rate.
I expect closing the door is sort of like one of those moments.
Nice and steady. Very slowly. There and,
0.67 millimeter mercury. Okay.
Right.
So that's 2 millibar,
Yeah, exactly.
I think.
Yeah, it's a little less than 1,000th of an atmosphere. So now we're pretty much ready to load hydrogen. And from this point forward, we're good to go to load hydrogen and do the shot. So,
Okay. So we're ready to go then? Or?
yeah, and we can converse some more after the shot.
And test in progress.
Yeah.
Do not enter the vacuum chamber.
And notice the serial number.
Serial number 1. Okay, we get this running. We get that running. Are we gonna clear out?
Yep.
Okay. Have fun, guys.
All right. We'll see you soon.
Excellent. We have a firing solution. We have armed, gated, and reset. Ready lights are green. High voltage is on. Mousetrap is armed and charged. The catalyst is in. Here we go. Armed. Here we go. Rolling. Impact. Pedals out.
3.86.
3.86 kilometers per second. 3.86. Shot time 12:06. 12:06.
So this is what it looks like with a regular camera. Obviously you can't see anything because all those bright lights are needed for the high frame rate cameras, and that's what these see. You barely get a glimpse of the projectile. There's a flash of plasma during the impact and then an ejecta plume. Now interestingly, there's a lot of speed variability in the projectile, so they actually have to have a series of timing gates that detect the projectile flying along at multiple kilometers per second and then trigger the high-speed cameras at the exact moment so that they actually get the impact rather than missing it. The high-speed footage is just one part of the test results. They obviously have to spend a lot of time getting each shot set up, and so they try to collect as much detail as possible. First of all, after the impact, they're going to physically analyze the rock, try to look at how deep the crater was, measure that, photograph it, try to reconstruct the amount of material kicked off. They have a series of thin foils around, which as debris spalls off and shoots off, they will make tiny holes in the foil, and so they can measure the distribution of sizes. And by having different thicknesses of foil, you can tell how heavy the objects are. And then they finally have big sheets that are lining the vacuum chamber. Those will collect tiny pieces of debris, and they try to bundle those up and then sweep all the dust into a little collector so that they can actually measure the size distribution from that. Meanwhile, the gun technicians, they have to go through a rigorous cleaning process after every single shot. Because if you think about it, at these high energies, these high velocities, even tiny pieces of dirt and debris are going to have a bad effect on your hardware and slowly break it down. The barrels get replaced over time because they are working at such high energies. I heard that some of the ones, they might only get 50 shots out of the barrel before they have to replace it.
Oh, is this the bow, the piston?
This is the piston, yep. It's been pushed into a high pressure coupling.
Yep.
And it's been switched in.
Awesome. Look at this.
That's it, yeah. The middle is hollow so that it can compress into the tapered part of the high pressure coupling.
Oh, I see, okay.
And create a seal. So you
Right.
can tell evident here it's dirty, and then you have bone white parts here.
Okay, so what are we going to say? We're like, hello, Chuck!
Scott, welcome
Hi.
back.
Are you welcoming to your parlor or whatever, your
this
box
is
of tricks?
my lair. Yeah,
Your
it's a lot
lair.
of fun, yes.
This features a gun which can go up and down.
Right.
Which, like many bad guys' lairs. But the difference is that your gun shoots inwards instead of outwards.
Instead of outwards, yeah.
Yes, so this is,
the Ames vertical gun range.
and it's unique in the world because?
Because of this ability to change the angle, as you see, it can not only shoot horizontally, but it can shoot vertically and many points in between, these 15-degree increments. No other impact facility can do this. They either shoot horizontally or they shoot vertically. But when you're looking at oblique impacts and how that affects debris dispersion and crater shapes and whatnot, this is very important.
Yeah.
So it's been a very useful tool for planetary geologists and geophysicists.
And this has been a useful tool for how many years?
Going on 60.
60.
Wow. Yeah, 1966 is when it
That is,
first
yeah.
came online.
Wow.
Part of the Apollo program. So
It is. We have an Apollo 11 sticker here,
yeah,
right?
yeah.
And a Viking, obviously.
So in its infancy, it was all about trying to understand the surface conditions of first the moon and then Mars, trying to better understand what the crater features were like and what we'd be landing on.
Right, and actually, this is your gas panel here, because this is critical. This is a two-stage gas gun.
Correct.
Right. And why do you need the gas panel? Because you got to put hydrogen in, right?
Correct.
Okay. So when you were setting it up, what you did was you vacuum first, and then you put helium in.
That is exactly right. This is kind of a schematic of the gun up to that high pressure coupling. The gun barrel would be down here.
The gun barrel comes out there.
So
okay.
this part here is what we fill with hydrogen. The gunpowder charge sits here. The piston would be right there. We use this panel to evacuate the air out of the tube and then backfill it with hydrogen. And then when we ignite the gunpowder charge, the piston comes down here, compressing that hydrogen to extreme pressures. And then when that rupture disc blows open, that's how
That's the second stage of the gas gun.
stage, right?
And that should be able to throw particles, objects, at 4 to 5 kilometers per second.
Upwards, close to 7.
As high as 7, and I guess that depends upon the mass of the projectile, or
Correct. And we test usually up into the 6s. The faster you go, the more stress it puts on the gun. You tend to erode it away faster. So unless you have a customer that has a lot of money, we tend to top out about 6.5.
okay. So but you could go
purposes.
faster if
If
there was a need.
Yeah, if there was a need, we could.
I mean, and so 5-6 kilometers per second. That is comparable to interaction velocities between asteroids in space, not say meteorites coming into low Earth orbit and hitting the space station. So these are sort of different regimes.
Correct.
Yeah.
Yeah, we low to mid-range, and then above that, we rely on computer models.
And so the things you are testing in here or have tested, give us some examples.
So, planetary defense. That's to do with the scenario. You discover there's a killer asteroid on a collision course with Earth. How can we nudge it off course so that it misses us? If you hit it too hard, you break it into smaller fragments, they still rain down on Earth, cause death and destruction on a pleasant day. So finding that sweet spot, we suspend meteoric samples representative of different types of asteroids.
Real meteorites.
That's right. Because you can do all you want with terrestrial rocks, but they're not quite the same as asteroids. So we like to use the real material and see how they respond to this momentum transfer, like shooting billiards.
Yeah.
And so that's a typical type of work that we do here. We've also been involved quite a bit in just fundamental understanding of impact physics. A lot of university professors, as you can see,
Yes.
We've had Brown University, Stanford, Alma College,
Johns Hopkins,
yes,
Southwest Research,
Alaska, University
and of course
Alaska.
there's some place called JPL.
Yeah, imagine that.
Yeah.
So a lot of effort's been put in over the years to try to just understand the underlying physics and phenomena when an asteroid or meteor hits a planet, moon, or a comet surface, what sort of cratering response you get from that.
Yeah. But you've done other stuff, right?
Oh yeah. There's been other projects. So this is my cheat
What
sheet
other
here.
applications require shooting things at targets at very high speeds?
A very good example was the Stardust mission. I should get a
let's go
prop.
to it.
Let's get a prop.
Yes, let's go
Early
get-
on in the Stardust mission, we knew we were going to be flying through the tail of the comet and encountering these microparticles at very high speeds, on the order of 5 kilometers per second. And the question was, how do you stop these tiny particles without destroying them?
Right. How do you capture space dust, which is moving at really high speeds? That's what Stardust was about.
Correct.
Capturing stardust.
And that proved to be very difficult. So we were using this gun to shooting a shotgun blast of microparticles. And first the JPL team was looking at stacked layers of very thin metallic foils, and that didn't work. Then they went to paper and plastic, all sorts of different films, kept destroying the particles. Then they went to different types of foams. None of that. They couldn't recover these particles. But what proved to be the holy grail, and there was much rejoicing, was the aerogel.
Aerogel.
This is a nice piece of aerogel
Yes.
right here.
So it looks like smoke, right?
Right. Solid.
This whole
smoke.
box is filled with this stuff.
This nice big slab of aerogel, lowest density man-made material. It's a thin diffuse silica lattice work, and that was allowed us to decelerate, capture these particles without destroying them.
And so here's a question actually. Aerogel, a lot of its weight is the air inside it. How long does it take to evacuate aerogel?
It's very porous.
So it's very quick. There's no like slow. Okay.
Right. Which is important when we have it in our chamber.
That's what I was thinking.
Because if you pump things down too quickly that aren't porous like this, they'll rupture, fracture, affect it. But here's an example. Unfortunately, the label is upside down, so pay no attention to that. But you can see the streaks of the particles. This is from stardust, where the particles came in, embedded themselves, and got trapped in the aerogel sample, which was then they painfully extracted them and analyzed them to
Again, grad students.
Yes, to determine their chemical and elemental composition. And so that was another novel use for this gun and being able to shoot it at very high velocities.
And I see these here. You shoot them at targets to see how spacecraft can survive orbital debris.
Yeah, this was kind of a simulated mock-up of the this one's a little bigger, easier to see, of like a cupola window on the space station. And you imagine a piece of orbital debris or a micrometeoroid impacts the window. What's going to happen? Are you going to have it catastrophically fail or depressurize the module? In this case, it survived just fine. But the spall, when the shockwave
spall come through on the other side, so it wouldn't be good for an astronaut.
No, they wouldn't have depressurized, but that astronaut would not have had a pleasant day. So that's.
I mean, and to be clear, right? This is the impact side, and that's the spall side, and there's a big difference in terms of the crater size, right? Because this is pushing in on this side, and it's pushing out on the other, so the wave tends to detach. What's that side?
More reminders. We simulated the extinction events, like the Chicxulub impact off the Yucatan. We've that was a couple decades ago, but we were trying to replicate that type of behavior, showing how we could tell that it was an oblique impact and not a normal impact by the shape of the crater.
Is this kind of crater thing where you would have different layers of sand?
That was an old technique before cameras became very.
This is before we had
high-speed digital cameras. So they would take these multicolored layers of sand with a little bit of epoxy resin powder, mix it in. We'd shoot into it, and afterwards they put it in an oven to fuse it. And then they would take these sections so they could see how where the material would go.
Yeah, and you can see this classic, folding over of the material here, because we see this at meteor crater, right?
Exactly.
Right. You can actually see the layers are curved and turned right upside down.
But now the cameras have gotten so good, you can capture all this
in real time.
Yeah. Let's see DART. There was a couple other missions we supported recently. The DART mission, the double asteroid redirect test. This was a model of the asteroid that was going to be encountered, and you can see where the impact occurred. So it was another momentum transfer to kind of assess how is that going to change the orbital characteristics of the.
This thing would have spun that up a little.
It was sitting kind of like that. They came in at a glancing blow.
You see this fragment off there like that.
So there was DART. Psyche mission. That's a recent one we've been working on. This is a metallic meteorite that has been machined into a cube.
So you took a very expensive metal meteorite and then machined it into a cube?
That's our researchers. We didn't do it, but
that's a lot of money, right?
Some of them are. They get nervous, because some of these can be thousands of dollars. But this was a fairly common, apparently, metallic meteorite. They formed into a metallic cube. We chilled it down and impacted it at liquid nitrogen temperature, so almost minus 300 degrees Fahrenheit or minus 170.
Right, because it's out of Jupiter's orbit, so you need
Exactly.
to have it super chill.
And so we would look at the difference in cratering response at the low temperature versus like our ambient temperatures here.
Yeah.
This is to give them an idea of what to expect when they get to Psyche in 2028 or whatever it is. And so yeah, we've used the gun for that. Let's see.
We get some other ones here. This is just like
Yeah,
Can I
those
take this
were
one?
sure.
because I notice. Look at this, right? The spallation on the back has sort of remained attached. So what this is a
A half-inch thick steel plate.
half-inch thick steel plate at 6 kilometers per second, and it's a 0.3766 grams. So that's not very much.
No.
Hundredth of an ounce. I don't know.
What's missing from the display, unfortunately, is that this was a demonstration of a. Have you heard of the Whipple shield?
Yes.
You know where you,
Yeah.
So that was a half-inch plate, and they had 1/8 inch, 4 1/8 thick plates stacked
In front of it. Yeah.
Yeah, and it stopped by the third plate, didn't penetrate through. Whereas this, it almost blew a hole completely.
Right. If you've
through.
got like a monolithic piece of hardware, it will shoot through. But if you offset, then it breaks up and it distributes the force.
Exactly, and so that was part of that display. I don't know where the other half went, but that was part of it.
Okay.
Let's see what else. Oh, we've got yeah. Oh, here this
This
was
is a shotgun.
this is another technique where we shoot materials. They can be the spheres that we shoot can be metals, they can be plastic, they can be glassy materials like
Yeah.
quartz. And if you shoot through like a thin diaphragm suspended above your target, it'll break it up into a debris
Like a Whipple
cloud.
shield?
Yeah, and so this is what the next layer of the Whipple shield would be experiencing. But it also kind of gives you a random distribution of particle sizes spread out over an area, so that can be a useful technique.
So how
as
big
well.
was the projectile in this case?
This was a 1/4 inch quartz sphere.
Quartz. Okay.
Quartz, yeah. And we shot through a little diaphragm that was about 3 or 4 feet above the target, and then it spread out in this kind of like a debris cone.
So you mean by a diaphragm, it was something that was roughly the size of the?
Yeah, it was a thin plastic. Let's see, do we have an example of
So, I
this?
mean,
Oh,
imagine that.
yeah,
It doesn't
here you go.
survive.
This in fact was the material right here. It's like a
Oh, so you would
7,000ths. You would attach it to a ring like this, and then you would suspend the whole thing
Oh, wow,
up
so
above
it's
the
that
target.
thin.
And boom, you shoot into it. Yeah, very thin stuff. But it's enough to shock those brittle particles and
right, and
cause
it
them to
shatters and it creates a shotgun.
Mhm.
We got a bunch of like little sabot or whatever the.
Yeah. This is our typical. Oops, that one's got a piece missing. There's a typical sabot for an 1/8 inch sphere. You can see there's 1/4 inch spheres in there. We span the gamut from about a 1/16 to a 1/4 inch in diameter for single particles, and then the microparticles, the shotgun blast. That's a different technique. They're tens of microns. Yeah, we always bounce back and forth between the English and SIE. It makes it interesting.
Yes, I'm bilingual too. On that front.
And in addition to our 2-stage light gas gun, we have a powder gun where we use a 300 Weatherby Magnum case. We load a predetermined amount of gunpowder in it. We launch the launch package that way.
And that's a whole lot easier because you don't need to pressurize
Right.
with hydrogen and
And
stuff.
we get up to 2.5 kilometers per second with this, and then from there on up to 7, we use the light 2-stage light gas gun.
That's pretty neat. Okay. Ooh, I like this one here.
Oh, that's
The car, playing cards.
Yeah, when we're breaking in a new gun barrel or making alignment adjustments, we have to shoot something. And then eventually, as we get closer and closer with our aim, we can sometimes get to
cut them in half.
Cut them in half, yeah, where you shoot from the side, and then the particle comes in from the side and rips the card in half. So that's when we know that we've got our alignment dialed in.
So how many shots do you get from like your typical gun barrel? I mean, how often do you replace them?
It varies depending on what
how hard you're pushing it?
Yeah, but it's usually we usually get 100 to 200 for typical conditions.
Yeah.
If people are really aggressive, want to go very high speed, it could be more like 50, but usually 1 to 200.
Wow. So if you're going hard, and that's a big piece of metal, right?
Yeah, it takes probably about a 6-month turnaround time by the time you have it. There's a lot of steps to manufacturing and breaking it in, so it's not something we care to do often.
Yeah. So anyway, is this chamber getting the pressure reduced now?
Not yet.
Not yet. They're set up.
Yeah, they're all set up. Everything's closed. The rock is hanging nice and steady. We like to keep the door closed.
There's a bunch of different cameras on this.
Oh yeah, they a little more horsepower than your cell phone. Some of them go
Are
to.
they? I actually think that cell phone might have more horsepower, but not as good a sensor.
Well, see, yeah, these can go. Some of them go to 1 million frames a second.
Million frames per second. That's insane.
Yeah.
Yeah. But they have nice big lenses on there and everything as well.
Right. So if you want a nice tight shot or a wide shot, depending on what you're looking at, if you're looking at the evolution of a crater and a debris field versus the initial breakup
and you would have these running at different frame rates. So some might get you 100 frames right at the instant, and some might give you a longer evolution, and so on and so
Correct.
forth, right? And then somebody has to assemble all these things together. Are these like a matched pair in terms of how they would be set up? Do you do like stereographic?
Yeah, we can do that. We have done that in the past. You put them side by side, and then you run both. You synchronize them, and then you play them back. And if you cross your eyes just right, you get a whole 3D kind of
you can
effect.
figure out where everything went. But yeah, this is like, how big is this chamber?
It's 10 feet tall.
Okay.
There's a false bottom in it as well. So it's like 8 feet by 8 feet in diameter. A little
Big
over
enough for a
400
person.
cubic feet.
And this is the original chamber and everything,
Yep.
right? This is all going back. And you were saying that some of these parts here come from like a Nike missile.
Yes, the whole ball screw drive mechanism for elevating the gun, that was from the
Right.
Nike missile launching platform.
So you
This was fabricated in-house to support it. The guns were all designed in-house. Over time, some of the instrumentation has we've modernized.
Yeah.
And we've got counters, but interestingly enough, a lot of heritage equipment's still hanging in there, still working. And what's kind of surprising is like these detectors. These are a laser-based intervalometer, the laser light sheet.
They're measuring the bullet as it flies down the
Right.
barrel.
When the bullet passes through the light sheet, it stops an interval timer, and we know the exact time of arrival and
So
the
you can
exact
trigger the
location.
cameras.
And from that, we can trip the cameras. And but these detectors, these are fairly new. They're only about 15 years old. They replaced a halogen lamp photomultiplier tube array that lasted 40 years, but they're already nearing the end of their lifetime. So newer technology, we're kind of living in that planned obsolescence era, where some of the newer things have got great capabilities, but they don't last as long. So we're always having to start over again.
This will be out of date in 10 years. Why would you want it longer than that? Buy a new one.
Well,
I get it. I mean, I saw the hardware in there that still has the tube amplifiers
Yep.
and stuff in it. That's, crazy. I love it. But yeah, I mean, this is your evacuated section, I guess?
yep, the gun barrel, the muzzle of the gun barrel would be sitting right here, so everything downstream would be evacuated.
Right, so this is all evacuated, going all the way into the chamber, and your bullet is basically free flying down here at this point.
Correct.
Right.
Yeah, the sabot separation occurs in here, and then there's a small aperture that it passes through, and then just the particle from this point forward, that silver Jules Verne-esque section. That's just from there forward is just
I'm just
the particle.
looking at the quality of the welding
Yeah.
here. It's like, it works. But so it comes out in a sabot, and that gets peeled off. There's a device here that probably splits it into the side so that the sabot doesn't
Yeah,
continue.
it's centrifugal force actually.
Oh, it's spinning?
Yeah,
Okay,
yeah,
so is this a rifled barrel?
Yeah,
then?
so if I don't know if you could see it, but if you were to look down this gun barrel, it would look just like the old James Bond
Okay.
movies. Here,
I think you meant. Oh, actually, I do see this barrel.
Here, I can throw a little more light on it.
This is where I have to bring the camera in. Yeah, I can totally see the spiral, but that is going to be really hard to capture.
Yeah, we have we're right now for this small particle size, we have the 22 caliber gun, but we'll be switching to a 30 caliber gun, which is a little easier to see.
So these are your other gun barrels down here,
right.
including some fresh ones.
Yeah, ones. Yeah, that we haven't broken in yet. So yeah, we'll be one more shot with a small particle. Then we're going up to a bigger particle because we want to measure the disruption energy to totally destroy the particle.
Right. And so so this goes on, and then the next part is this, right? Which
Correct.
It mates via this section here. And here.
Yep.
And fancy hydraulic coupling for super high pressures, I guess. And then that screws into this.
Mm-hmm.
And this thing here is like a. Wait, is this your traditional gun barrel section?
No, well, yeah, this would be the first stage. Yeah.
Right. So this is where your piston is.
Right.
Right.
So yeah, we load the piston right here, gunpowder charge in here, and well, in fact, you can see the piston sitting there.
Oh yeah, some of it's already in there, ready to go. Great, ready to get up to speed and stop very quickly.
Yeah, that's right. That's why this thing is so beefy here.
Yeah, right. So this is a monster if you think about it. I mean, it's basically taking the force of that explosive charge and trying to corral it
Yes.
to the next stage. It is kind of crazy. So, wow. So now, what else do we want? Is there anything else we should talk about here? I'm just
Let me look at look over here if there's any other. I could mention other projects we worked on were like Cassini, Mars rovers. These were assessing the potential damage that could occur to a spacecraft while traversing to its destination.
like Saturn's rings.
Yeah, well, Cassini
down.
was like from Earth to Saturn. If the spacecraft got hit by a micrometeoroid, how much damage might you expect? And do you have adequate shielding, or do you need more? Right. So we've done some simulation of impact on spacecraft components to assess that.
So yeah, I mean Cassini. Okay, that's one. It has to survive, and so of course. Did it for Cassini. Now every spacecraft can use that knowledge, right?
Right. We did that. Cassini, the Mars rovers, that spacecraft as well. So JPL would typically come up and say, "Hey, we've got a component we're concerned about. Can you shoot this size particle, this speed, and tell it and show us what the results are?" And then, okay, yeah, we're not concerned.
Right.
Ooh, we need to reevaluate our shielding idea.
Right, and I'm sure it's hard to think of a new environment that might come along. That's the thing. There might be new materials, right? Hey, we love our carbon fiber composites.
You remind me of something. Yeah, new material. We were there was a group. It was an Ames Stanford joint effort before COVID. They were looking at in situ building materials. They were taking making this bioconcrete with some bacteria-based binding agents to make basically concrete out of regolith.
Right, from like lunar regolith. Right?
Exactly.
Yeah. So could you build like a dome on the moon that would survive these? Right.
So they were creating these, concrete-like structures, biocrete structures, and we were shooting into them to see how they respond to impact. So
again, this is the perfect kind of thing for it, right?
So look over again. L-Cross mission, that was similar to Deep Impact, where we used an impact event to excavate material to.
Right, and it would fly through the plume.
Right. So you could
you probably wanted to test the sensors even.
We replicated the whole kind of impact event here, lighting conditions and sensor arrays to kind of see how they would respond. And so you have not confidence that your mission's going to be successful.
Yeah. Okay.
I sort of like this old school gear here. Do you want to talk about it?
Sure. So this is our firing panel. You have components, the oldest one from 1946, all the way up to new modern electronics.
What's the oldest part?
The oldest part would be a vacuum tube located in the high voltage discharge area for firing the gun panel. Now, it's original equipment from 1960s when they made the gun, and then we've incorporated new timing circuits, new counters, so that we can get the 10 nanosecond resolution for optimizing our shots and camera.
So there's 10 nanosecond resolution for.
Yes, we have 10 nanosecond resolution that we've timed so that we can trigger the cameras, fire off the mousetrap, and get the shot going. Mm-hmm. And once we fire off the projectile, it'll go into our intervalometer stations. So we have 3 laser stations that will detect distance, rate, time From there, we can get the velocity, we get the moment of impact, and we can also trigger JP's cameras so we can identify what the optimal amount of frame rate would be to capture that in slow motion.
Okay. So this is basically, you've got, okay, I'm trying to figure out this is a sequencer here that's giving, I guess it fires off a bunch of different signals in sequence with specific
It does,
delays.
yes. It works off of an open-closed relay system.
Yeah.
And from there, we can trigger the cameras, we can get the firing going, we can turn off the lights, and it will terminate the sequence, giving us a termination time. So we have a moment of fire to the moment of the termination of the test.
Okay. And these here are,
These are counters, as we have two fail-safes here for timing. So we have our intervalometer stations that the projectile passes through 3 laser beams. As it passes through the laser beams, we monitor the times. And then we also have an oscilloscope that monitors the trigger, the times, the moment of fire. And then we have a quartered proportional time delay generator that gives us a delayed time output to trigger the cameras or any other equipment after the fact.
so this is like you fired the bullet and there needs to be a specific delay before you start shooting
Yes.
the
Everything else is timed off of the delay from the moment of fire and the moment the intervalometers detect the projectile.
This is some really cool old gear, I'm gonna see.
It absolutely is, yes. I've worked on these vacuum tubes and I've worked on modern electronics. And part of my job here as the instrumentation technician is to make sure all of this works in sync with JP's cameras and any other instrumentation that the scientists will bring into the vacuum chamber.
I like how this has an old NASA work logo on the.
Absolutely, yeah.
And the thing is, that was relatively new parts for some of these, right?
Yes,
some of these parts are old, are like from the 60s.
Yes,
They're-
you're talking about this panel weighs
Right.
about 60 pounds or so.
Yeah.
And we have the proportional time delay generator, and the actual computer for this is about the size of this keyboard on the internal. But we like to maintain the same style. And
Yeah. Oh, it's definitely very, very cool. Thank you.
I'll be honest, it seemed that wherever I went, there was something cool that I could learn and talk about. And there's actually going to be a ton of B-roll video that I might share on my Patreon. But yeah, we got ready for the final shot of the day. And this one they hoped would disrupt the object, shatter it into many smaller pieces. So, of course, they had to clear the room while they installed the charge and safed the system, got it ready. The chamber was set up with a new meteorite. I added my own camera to the mix. The firing room was locked down and we waited.
See it.
Oh,
Yes.
That was a good one.
Yeah.
The final shot of the day had used a ball which was twice the diameter, therefore 8 times the mass.
4.45.
4.45. Spicy.
So while my iPhone wasn't quite as fancy as the other cameras, it was pretty authentic. Yeah, that's how fast it happened. Now that phone was shooting in high-speed mode. That meant 240 frames per second, and I could hear the other cameras laughing at a mere 240 frames per second. But it does give a little more detail when you watch it this way. There is the tiniest hint of a flash, which becomes much more obvious in the real high-speed cameras. And remember, they were actually intentionally running the gun at main belt asteroid speeds rather than, say, low Earth orbit speeds that this thing can achieve. And of course, it's worth remembering that while these events took a fraction of a second to capture in the high-speed cameras, the actual setup of this took hours, and the processing of the data, both from the images, from the debris that's captured, and all the other stuff, that is going to take months or even years. But perhaps one day it will be crucial in understanding how the human race can change the orbit of an asteroid. Right now, as I'm recording this, we have one of the highest chances of an asteroid impact ever observed. 1 in 67 for an object which could be anything from 8 to 50 megatons of yield, equivalent when it hits the Earth, potentially in 2032. It's probably not going to happen, but we would like to know how to deal with it when that eventuality arises. And so thanks to NASA for letting me come out and watch this. Thanks to the research team, George and Dan. Thanks to Charles and Freddie at the gun range itself. And finally, thanks to my daughter Sky, who was there as the camera and sound person trying to capture this amazing day. I'm Scott Manley. Fly safe.